one is when you throw the switch to B, all right, it's no longer charging up, so now it's going to be discharging. This is already charged up, so what's going to happen is the current is going through the resistor, it's going to decay, which means that the current is going to slow down, which means that it's going to start to lose its charge. All right, so this one is an easier one. Okay, so because this is not in person, if I could find a way to actually test you guys so I can see the details of what you're doing, this is one of the things that this would be a test question. Okay, instead of giving you the charge up equation, which can be done using calculus, except it works better if you're using differential equations, which is not required. This can be done using calculus. Okay, this is normally a good standard test question so that I can see your reasoning as well as I can see your mathematics. So he said discharging a capacitor, once again, you have to use the Kirchhoff's rule. There's going to be a voltage drop as the current is going across there. There's going to be a voltage drop across the capacitor as it's discharging. And then you kind of turn it into a differential equation. This is current is how fast the net charge per second or how fast the charge in a moment. And then immediately, this is a first order differential equation, or it's just simple calculus. You use the integral, and then this is the equation that you come up with. Okay, so let's focus on the meaning of this equation. Once again, the meaning of this equation is Q naught is going to represent the maximum amount of charge that it can hold. So this should be Q naught. And this is your net charge axis. All right, so this is your time axis. This is the net charge. And obviously, this is an exponential decay, so this one is straightforward. And the equation works out. All right, a couple of things. I hate to do this, but we have to do a little bit of math. I know most of you guys are university students, which is good, but some of you guys are community college students. And I'm not entirely sure why students usually struggle. I mean, most of you guys are taking calculus, calc 2, calc 3. Some of you guys are taking differential equations. But it's kind of annoying that still some of you guys struggle with equations like this. This is so weird. For example, if I were to ask you to find R in this equation, just isolate R, some of you guys struggle with it. All right, so let's do this, just get it done with. And just want to make sure that all of us are on the same page with this one. Got to do a little bit of math. All right, so this one is a charge up equation. So we're charging up the capacitor. All right, so you're not only building up the net charge, but also the voltage is building up, whatever that means, across the capacitor. So that's what you got. This is your time axis. And this thing is going to build up to its maximum value or the maximum voltage. Okay, so either way you look at it, both equations are the same. And so the charge is building up, voltage is building up. All right, so either you use, here's the maximum value. All right, this is your time value. This is your capacitive time constant. All right, so this is the maximum value that it's going to build up to. Or, put differently, this is the maximum voltage that the capacitor is going to be able to store within that time period. I'm giving you two variations. All right, depending upon the multiple choice test question, you have to use one of these equations, and both equations look the same. And so this is the value that the voltage is going to have at a given point in time, or this is the charge that it's going to hold at a given point in time. Either way, you're fine. Okay, and sometimes they will give you all these values. All right, so they'll give you the time, the maximum charge that it can hold, and the amount of charge that it's got at that point, give you the capacitance value, and then they will say, hey, find the resistance. All right, so you end up getting these weird variations. All right, so just solve for R. All right, let's take a couple of minutes to do this problem. All right. All right, so let's solve this for R. Set it to save time and fast track this one. So isolate R. And now we get a negative value in the exponent, so I don't like negative values. So just invert that, get rid of the negative value by inverting both sides. Now I get rid of the XE by taking the natural log of both sides. Natural log of 1 is going to be 0, so that drops out. And now isolate R by switching those two terms, and R is isolated on the left hand side. So that's the approach. Let's work on problem number 7. Let's list everything first. So we need the capacitance time. So it's going to take 8.3 seconds for it to discharge. And then it's going to discharge to 63.2% of its maximum value. So basically isolate C, get rid of the negative exponent. That's one of the things that I like to get rid of. Makes life easier, so invert both sides. Take the natural log on both sides. And then switch the terms, to get C on the left-hand side. And then that's it. Just plug in the numbers.